Hi guys. So today we're going to look at absolute value inequalities. So very similar to what we just did with equations, except now we're going to be considering where it's above and below these graphs. So we're going to start by looking at this by graphing, just so you guys can see visually what's going on here. So I'm going to start by graphing the absolute value of x minus 2 minus 1. So that's been shifted right 2 down 1. And it has that same slope of 1. And that's not a very good straight line. But you get the idea. All right, so what we're looking at then is this graph in comparison when it's greater than 2. So the line y equals 2 is the straight line that's a horizontal line right there. So where it's greater than would be where the blue graph is above that red line. So that blue graph is above that red line here and all of here. So we're going to write this two ways. We're going to start by writing this in inequality notation. So in inequality notation, this would be true when x is less than -1, or this would be true when x is greater than 5. So those are the two places where this is happening. In interval notation, what that would look like, it's from -infinity to -1, and then from 5 to infinity. So now we're going to go ahead and look at this second one. We're going to start by graphing that absolute value. So that's shifted left 1 up 2, same slope. And then we're looking at where that graph is less than y equals 3. So less than is going to be where it's below, and it is below in that part right there. Well, if I were to write this one in inequality, it's going to look like a different inequality. This is going to be one of those compound inequalities where -2 is less than x is less than 0. In interval notation, that would be from -2 to 0. Now the difference between these two equations to start was our inequality symbol. So this left graph, we were looking for when that function was above that line. This left graph, we're looking for where it's below the line. And as in turn, those created two different types of inequalities. So in general, if we have an absolute value that's isolated and it's greater than a positive number, when we solve it, we are then going to set up two inequalities. We're going to look for where x is less than -a and where x is greater than a. If we're looking at a case where x is less than a positive number, we're going to split this into two inequalities, except we're going to look for where both of those things are true. This is an and case. Kind of the way I usually remember it is I like to say if it's greater than, it's greater. Okay, it's not greater, it's greater than. So the greater than equations are going to be our or inequalities. So let's look at the algebra behind this so you can see a little bit more what that looks like. Following very similar steps to what we did with solving our absolute value inequalities. Get the absolute value by itself first. So once my absolute value is by itself, then I can look at what sign I have. So I have an absolute value that is greater than a number. So this is going to be an or situation. So two scenarios. X plus 1 is greater than or equal to 2, or x plus 1 is less than or equal to -2. So on that second inequality, we changed two things. We changed the plus or minus sign, and we also flipped the inequality symbol. Very similar when you're used to solving inequalities. If you divide by a negative, you flip the sign. So when we change that to a negative, we flip the inequality symbol as well. So then we're going to go ahead and solve both of these. So I get x is greater than or equal to 1, and I get x is less than or equal to -3. So since this is an or situation, either of these things can be true. So I'm going to go ahead and plot this out on a number line. So here's -3. We want everything that is less than or equal to it. We also want for x to be greater than or equal to 1. So this is what my inequality is going to look like. So then we're going to write our answer in interval notation. So in interval notation, this would be from -infinity to 1. It's going to have a bracket because it does include it. Whoops. Sorry, that was -3. And then it's going to be from 1 to infinity. All right, very similar on this next one. We're going to get the absolute value by itself first. So then we're left with the absolute value of x plus 3. And now when we divide by -2, we flip the sign. So there's inequality number 1. So x plus 3 is less than or equal to -1. Since we're dealing with less than, these are and. So we're going to have two inequalities. This time it's and. We're going to flip the sign and change the plus or minus. And those are my two inequalities that I'm going to work with. So I get x is greater than or equal to -4. And I get x is less than or equal to -2. So again, I'm going to plot this on a number line and make it a little easier to see. Here's 0. I'm looking for x to be less than or equal to -2. And I'm looking for x to be greater than or equal to -4. So the overlap of those two things is my solution, which, man, I am flipping my numbers, -4 to -2. So the overlap is the solution on these and circumstances. So and we're looking for where they overlap, or we're listing both possible values. All right, now those were always when we're looking at it in comparison to a positive number. So let's see what happens when we're looking at it in comparison to a negative number. Again, we still have to get the absolute value isolated before we consider anything, because depending on what that is, it's going to change what we're looking at. So now that absolute value is by itself, but now we're looking at an absolute value less than a negative number. Well, an absolute value is always going to be positive. That means it will never be less than -5. So there's no solution to this one. All right, now let's look at the same question, but let's flip the sign. Again, isolate the absolute value first. We cannot make this decision just based on the fact that there's a negative to start, because if this was -4 instead, that would entirely change our problem. So always isolate the absolute value first. Well, now when we look at it, we have an absolute value greater than a negative number, and that will always happen. So if you end up with a negative, save yourself the time. Don't worry about your ands and your ors and setting up your inequalities. If it's less than a negative, it's no solution. Greater than a negative, it's all real numbers. So absolute value is less than a negative. That will never happen. Absolute value greater than a negative will be everywhere. All right, so now let's look at E. So E is kind of a special case. Again, isolate your absolute value. So what I'm looking at now is when it's greater than 0. Well, we know that it's always going to be a positive number, and positive numbers are going to be greater than 0. The problem is that our positive numbers, well, all of these solutions won't be greater than 0 because one of these solutions is equal to 0. Since this is just greater, it's not or equal to, there is one answer we have to exclude, and that is the value that makes it equal 0. So when x equals 4, my answer would be equal, not greater, so x cannot equal 4. So this is all real numbers except for 4. So -infinity to 4, union 4 to infinity. All right, looking at F, again, get the absolute value by itself. When we divide by -1, we flip our sign. So now we're looking for when this is less than 0. Okay? If it was just less than, then it would just be no solution. But it's not just less than, it's less than or equal to. And because it can equal 0 at one point, x equals 4 is a solution, and it is the only solution in this case. If this was just less than and there was not the or equal to, there'd be no solution. But because it's an or equal to, we do have an extra possibility there. So whenever you're dealing with 0, again, just pay attention, make sure your or equal to's are giving you your full answer. All right, so we're going to look at 2 more algebraic examples and then 1 application. So same process here. We're dealing with less than is and. So this is going to be an and situation. The absolute value of 2x minus 3 is less than x plus 1, and the absolute value of 2x minus 3 is greater than negative x minus 1. And I should probably just go ahead and take off my absolute values. Apologize, step ahead. All right, so let's go ahead and work this one out. So I've got 2x minus 3 is less than x plus 1. So x is less than 4. And 3x is greater than 2, so x is greater than 2/3. So since it's and, we're looking for the overlap. So here is 2/3, greater is this way. Here's 4, less than is this way. So the overlap between those two is from 2/3 to 4. All right, then last algebraic one, let's go ahead and look at h. What I'm going to do here is I'm going to rework this right side. So we talked about this when we got to graphing, where if you had a coefficient on both of those, that you could divide that out and we could put it outside the absolute value. So we're going to go ahead and do that just so these are more comparable. So now that both of these have that factor of 2, I'm just going to go ahead and divide both of them by 2, just to make it a little simpler to see what's going on here. All right, so now if you consider this inequality, we can consider this algebraically or graphically. So graphically, let's look at what's going on. I'm going to go ahead and graph that right one. So it's shifted right 2, it's opening down. Then the absolute value of x minus 4, that's shifted right 4 and opening up. Is there a place where this blue graph is greater than or above the purple graph? Okay, no. So this has no solution. Now, if you didn't want to draw the graphs, if you want to think about this algebraically. So an absolute value is going to give us a positive number. So this is going to be some positive number times a negative, which is going to give us a negative number, because a negative times a positive is negative. We're looking for that to be greater than an absolute value. That absolute value has to be positive. And a negative will always be greater, or will never be greater than a positive number. So that's why there's no solution to this inequality. All right, last thing we're going to look at is just an application question. Again, this is one where you can probably read it to determine your answers, but we want to be able to write this as an absolute value so that we get used to seeing some of these applications when we get to some more complicated things. So it says a machine cuts boards that are 3.25 meters long. They've set an allowable amount of air of 0.02 meters. So if a board is more or less than that away, then we're going to throw it out. So to find the list range of acceptable lengths, we're going to take whatever size the board is, and we're going to subtract 3.25. If that air is less than or equal to 0.02, then we can keep the board. So that's how we represent this with an absolute value inequality. Now our solutions here, if I would actually work this out, or what you would expect them to be, this would be a less than, so it's and x minus 3.25 is greater than or equal to 0.02. So I'm looking for where x is, negative 0.02. I'm looking for where x is greater than or equal to 3.23. And I'm looking for where x is less than or equal to 3.27. The overlap of those two things is from 3.23 to 3.27. All right, so that is absolute value inequalities.